Good morning. We talked about path integrals last time, so here's a short summary of coherent state path integrals. The goal was to start from the master equation, which you see in the first line, and then to derive for that master equation a path integral formulation. There are many ways of doing this. The one I find the most straightforward is to say we define a marginalized distribution where instead of the initial condition in terms of a particle number n0, we marginalize distribution over a Poisson distribution in the beginning, and then you have a continuous variable x, which is basically the mean of the initial Poisson distribution. And then for that continuous variable, you can write down the backward master equation. And from that backward master equation, because it is a differential equation, a partial differential equation, there's a quite straightforward way of deriving then the action and the path integral. And that action has the typical form. It has an auxiliary field that's called Q. And this is dotted into the time derivative of our continuous variable x. And then there's an operator that describes all the reactions that we have in the system. And those reactions here are written in a general form, which encodes not just a single reaction, but many reactions. And I will talk about this a bit more today. So let me start from here. So coherent state path integrals for the reactions, and I want to have now a state where I have many species, and I call them a sigma, where this sigma runs from 1 over 2 up to the total number of species that I do have in my system. Then instead of the simple case that we considered last week, we now have a vector that's characterizing the state of my system, and this vector is encoding the number of particles for each of the different states that we have up to the total number of species. And the way we want to look at that is in terms of the marginalized distribution. So this then would be in terms of the whole set of these mean values, x1, x2, up to xs. Okay? And that's, in general, just a tensor product of all the different states. So it's the occupation number for each individual particle type, where I marginalize the distribution, such we talk about the means and not the initial particle numbers. Okay? And as before, we use a Poisson basis. And this now for each individual state, that means each of those is given by x to the n over n factorial e to the minus x for all the species that we have. Then we have our ladder operators, and they simply then get indices, so it's not getting any more complicated. All you have is that you add indices such that the creation or raising operator is simply the value of the mean x for species sigma, and the lowering operator is the derivative with respect to that particular species. Okay? And what we want then is we want to rewrite the master equation that we have for this marginalized distribution, n of t, at some initial time tau for these marginalized variables x. And that is our Q matrix acting on the marginalized distribution, right? And then it's just a matter of repeating all the steps, and instead of writing it for one variable, I just have the tensor product of all of them. So in the end, this will give rise to an action S now, depending on these continuous fields, which are now vectors as a function of all the times along the path. Then we have the complex unit, and our auxiliary field Q becomes now a vector field. And that is, as before, a time integral between the windows I'm looking at, so t0 and some final time t. And then the structure just becomes a matrix operation, so I have the transpose of my vector q dtx. Oh, sorry, I should write here d tau, because that's my integration variable, minus the operator that comes with the Q matrix as a function of the continuous variables x and my auxiliary vector Q now. Okay, and the reactions we can look at is now a whole set of reactions where I'm going from sigma equal 1, so to the total number of species S. And the reactions have here some multiplicities, k sigma, a sigma, and that then turns with certain rates gamma, which are the rates for all these different reactions, also from sigma 1 to S, L sigma, A sigma. And if you want to specify the Q matrix as a function of the number of individuals of each of the species, so n is a vector and m is a vector, then you do have now this reaction that happens with a rate gamma, and I have to pick K1 out of M1 up to Ks out of Ms. So it's a combinatorial factor that you get by arranging who is reacting with whom. And then you have reactions which are such that you have to match the number of particles that are getting created and destroyed minus delta Nm. Okay? So as you see, this is more of a writing exercise than actually conceptual advance. You just have all the different terms for vectors instead of scalars. Okay, and in the following, we write it in such a way that I use here the objects M1, K1, which is counting down M1 to M1 minus K1 plus 1, and the same for all the others. So MS, KS, and the same kind of Kronecker deltas. And in the following, I'll forget about the tilde here and call the gamma tildes gamma again, just for notational convenience. So when you translate this to a Q operator that appears then in our path integral, the rule is really very simple. You read the reactions backward in time. So let me first write what you have here. You are deleting a particle of type 1. You do this L1 times according to this rule, and you repeat doing so up to species L, Ls times, and you're creating them here then in this order, A as dagger Ks up to A1 dagger K1. And in order for that to map with the corresponding master equation, where you have the diagonal elements being all the processes that get out of the state, I have to complement this operator here by the one which is identical to this one, but just has the A daggers replaced by the A's. This is then minus A1 K1 up to AS KS. Right? So that's the recipe of writing down the path integral. Maybe we want to do an example. So let's do an example, and you help me then to set this up. So we consider a reaction where you have 3 species, and we call them A, B, and C. And now we say that we want to have a set of reactions, which in general is K times A plus L times B, going to and going back, MC with rate lambda and with rate sigma. Okay? So in my terminology below, this would be 2 different reactions, but I'm writing here them as one, because typically that's what you mean by having reactions going forward and backward in this way. So what's the Liouville operator? Well, it's just a copy exercise. So we have lambda times A dagger to the power K. Right, this is this term. And we have then B dagger to the power L. That's this term. I'm creating those 2 particles, types. And then I'm having here that I need to delete a particle of type C m times. And this term here is to complete the reaction with the exit processes, so A to the K, B to the L. That's the first reaction, and the other reaction is just backwards. So I have plus sigma, and then I'm creating MC particles, and I'm deleting the particles of type A and B. and I have to complement that term with a c to the n. Right? That's how it works. So now there's something for you. So A going to 0 with rate mu. I call this death. B plus B going to B with rate, B going to B plus B with a rate sigma. I call this a birth event. And we have also A plus B going to A plus A with a rate lambda. And let us call this predation. So a particle is killing a B particle and creating an offspring of its own type. Okay, now what is the corresponding operator for Q? Right, so your job. So you read this here backward. Here you create a single A, right? So this is a dagger. There's nothing really to delete. So that's an operator to the power 0, which is a 1. And then I have to complement the A. Take the next one, plus sigma. And I'm really leaving it up to you. So who dares? Come on, don't be shy. Can only get it wrong.
You mean the second one, right?
Yeah. Yeah.
So reading backwards is killing 1B.
Mm-hmm. You're killing, so here, you're killing this B, and you're killing that B as well, right? You're killing...
I have to kill 2 and give birth to 1.
Yeah, that's what you do, right? Because you kind of make an empty site.
Okay.
So you
I just need 1B, I kill it, and then...
So you kill 2 Bs,
Yeah, okay.
and you back create one of them. And then you have to complement again with a B.
Why always 1B? And that's like the...
That is the same, okay, not always 1, it's the same order as the prefactor. So if you look here, you have A dagger to the K, B dagger to the L.
Yeah.
Then the second term always has to be the annihilation operator complement. And this is in order to get the Kronecker delta NM in the diagonal of the Q matrix. Okay, so this is the first term in the master equation, and that's the second term where you have all the exit rates. Same here. So what about this one? Plus lambda. Yeah?
We have A dagger, B dagger,
Yeah.
A squared minus AB.
A dagger, B dagger, A squared minus AB. All right. So you got it. Okay, that's how it works. And it's very simple. Once you know these rules, you can forget about all the derivation. It's a very standard way of deriving it then. Yeah?
I'm still puzzled about what's on the second blackboard. When we have now species, we transform it into the Poisson basis, that we just get a product state. I wondered why that is. You know, what the N1 to the NS, that's a product, like tensor state. And
It's basically the same as in quantum physics. You define that as your state. And all you want, really all you want is this. You want a state where you can count how many particles of type 1, 2, 3s you have in your system. And then you need to find a proper notation. That's all you need to do.
So I agree up to the first equation side, basically, where you wrote it as a general expression.
This is just notation.
Is it really? Because
Yeah.
I think, okay, because that's
It's just notation.
confusing.
It's just notation. If you write it down in terms of those things, then you have P of n vector, T, n0 vector, tau, and then you have to sum over all the marginalized distribution in the beginning,
Or the initial condition.
all the initial conditions,
Times the respective cost.
times the respective Poisson distribution, and your assumption is that there is no correlation whatsoever in the initial states.
Okay.
You don't really assume that. It's a definition of a marginalized distribution. You can do what you like in defining a new distribution function, but physically it corresponds to saying that initially the particles are put there at random in terms of their absolute number. That's why you have a Poisson distribution. And at random also with respect to each other, you don't encode any kind of correlation in the initial condition.
And I'm also puzzled, why do you call it marginal distribution? I mean, when we marginalize, I usually integrate out 1 degree of freedom.
It's a name. It's a name.
I wouldn't think of a transform distribution.
Call it out as you like. We chose that name.
Okay.
And yeah. Maybe you have a better name. So up to now.
I don't want to say that, but it's just
No, it's
marginal has a meaning for me already in a different
Yeah,
context, you know?
yeah.
Probably for you too.
yeah, it does. It just means you sum over one variable and you reduce the distribution function by this one variable.
Exactly. That's not what we're doing. We have an X now.
Yeah. So it's a name that I and my student at the time came up with. We can still change it. So I don't.
I don't want to.
Yeah. It's take it as a name, right?
We can always put the philosophical confusions into names.
Yeah. So I don't really have a special connection with that particular terminology. So in the end, this is not the only choice, right? This is a choice we make. And as you see from the structure of the ladder operators, that makes it a very, very convenient choice. You could also take this, x to the n. Then it's less convenient to write down. Okay? So, but one thing you should always note is that x is not a physical variable by itself. It's a trick by which I transform this into a PDE and then derive a path integral. And as you remember, there's a subtlety. When you want to then rewrite the corresponding path integral as a Langevin equation, you cannot. Okay, then also for the Kramers-Moyal path integral, which I must say I really favor because it has a more transparent structure. Okay, and here again, Kramers-Moyal path integral is a name we came up with because coherent state path integral was the analog, and you could also give it a different name if you like. So there, the action that you get is a much nicer object, and the reason is that now you really formulate the action in terms of the variables that correspond to the physics of the problem. So this is really the particle number that you have. And this is then also a integral, same structure as before, over the time window you're interested in. And then the first term has the analog structure. It has our auxiliary field. And now just let me not write the vector indices. Transpose means this is a transposed vector. Dtor n. That's always the same structure. It just comes from the first order of the corresponding dynamics. Then we have minus gamma of n. Okay, this is this reaction term on the bottom here that is of the same structure as before. And then the two terms in the master equation are then represented by those terms here, n tilde t delta n minus 1. And they're the same as before. One is the processes that get you into the state, and the other ones are the processes that get you out of the state. And remember, this particular structure that we found here is due to the fact that you need to write the delta, Kronecker deltas, in terms of corresponding integral representation, and that's how this came about. So with, let's say it again, gamma of n vector is now gamma, and here I already replaced the tilde by a non-tilde, and then you have n1 k1 to ns ks, and you go down in the product up to n1 minus k1 plus 1, etc. Good. And in the exercise classes, you will study an example of how to write down a path integral for that. All right, for what we want to do next for us is we want to include the spatial dynamics. Okay. Up to now, this is just reactions, meaning I'm kind of assuming that all the particles are in a well-mixed environment, and diffusion is not a limiting factor. They just all react specified by those chemical reactions or dynamic processes. Good. Now let me go to the slides. Okay, so directed percolation is one example where I didn't really introduce space yet. I will do so for a different thing. So this is a famous event in soccer history.
Бери кросс и роту. Ну, настроение хорошее. А вот, замечательно. Только этого еще не хватало.
Okay, so they play rock, paper, scissors, as you noticed. And you can play rock, paper, scissors, which is a reaction, right? Rock and paper and scissors win against each other in this kind of rule. So, as you know, there is this rule of cutting, covering, and blunting rock, paper, and scissors, and this is a cyclic rule that you have. Now you can play this game here not just between three individuals, but actually on a lattice, okay, where you have three species, not these three guys, but three abstract species now, A, B, and C, and they cyclically interact with each other. So what do I mean? I mean this. So you have here three species, call them A, B, and C, or red, blue, and yellow. And then there's now various reactions. That's not quite the rock, paper, scissors game. It's kind of an intermediate version where you say that first there's a dominance event, a contest competition. A meets a B, and by meeting that opponent, A is dominating over B. That means it creates A, or it remains A, but creates at the neighboring site an empty site. So the individual B is killed. And you do this in a cyclic manner, like in the rock, paper, scissors game. So here you then have B dominating over C. So you keep the B and replace the C by an empty site. And finally, you have C dominating back over A. So you keep the C and replace the A by an empty site. That's the competition, the contest competition between the three species. And then you say you also have scramble competition that comes from game theory or bacterial competition system, where you say now, well, there are these empty sites that are available to you, and now you actually run the race for occupying those empty sites with your offsprings. So here the rule is if A is facing a neighbor that's empty, it can give birth to another A individual. So you have two A's, the same for B, the same for C. And that's a model people have studied before, and it was invented by May and Leonard as one of the classic models of spatially of games. What we want to do is to add this here to the game, namely that now A and B or B and C or whatever you have, they may flip their position. So here in that particular case, you have a mobility epsilon which swaps C with A. All right. Before that, let's look at the well-mixed dynamics of that. So this would be just the reactions we have on the board now. I gave you the reaction kinetics. So as said, there's contest competition. A dominates over B with rate sigma. And there's birth. A gives birth with rate mu. And then the rate equations are very simple, right? So if you say the change of A is birth if you have an A and you are having nobody next to you. And 1 minus rho, where rho is A plus B plus C, is the likelihood that you have an empty site next to you. And the other reaction is that if you meet a C, then the C is actually dominating over you with the rate sigma. So this will give you a minus sign in the rate equations. And that's the first equation. For the second and third species, B and C, you just repeat the same analysis. You give birth if there's an empty site, and you lose in a cyclic manner against your opponents. Okay? You can now study that as a system of ordinary differential equations and plot them in phase space. Phase space means the space in which you plot the concentrations of species A, B, and C. And when you do the analysis, that's not something we do here, but it's interesting on its own. When you do that, you find that there's this yellow manifold onto which at first the dynamics contracts. So whatever you start here in this phase space, it will quickly turn to the reactive manifold that's in yellow here. That's a slow manifold of the system, and on that slow manifold you have then the next time scale of dynamics unfolding, and that is such that this point here is unstable, so you can't reach that, but you go instead in spiral circles to the boundary, and you move along the boundary until you get close enough to one of those points here, and then you are in an absorbing state. You will never reach those points, though, if you write down a continuum version of that, because this is like an exponential decay, which goes to 0 but never reaches 0 unless you are t equal to infinity. And these orbits here are the same type of orbits where you only reach the absorbing states in asymptotic fashion. Okay? So that would mean if you were to just guess what the dynamics is, that the system dies out, right? You can also guess how long it takes you to die out if you have a stochastic system. Any ideas? Okay, this is an exponential decay. So roughly speaking, the particle number decays exponentially to 0, and it reaches an absorbing state if n of t is of order 1, right? That means you expect that the time for extinction scales like the log of n. Just invert n of t equal 1 and evaluate for t. Indeed, that's the case. If you do the stochastic dynamics of that, you will always reach an absorbing state. Well, what do you get when you look at the spatially extended system, so playing this rock, paper, scissors, or May-Leonard game on a lattice? Then again, you have three individuals, A, B, and C, and what's changed here from right to left is that you change the diffusion coefficient. The diffusion coefficient is high on the right. So you strongly mix, and in the left you weakly mix. Yeah?
The diffusion coefficient is the one where they swap.
Swap. Yeah.
They can also swap the place with the empty state.
Yes.
So there are empty squares somewhere sometimes, right?
Yeah, and you might faintly see them. Those black spots you hardly see. So also that. Yeah. Well, this is what you get. So if you mix not well, you get this. The better you mix, the larger the length scale on which the patterns appear here. And in the end, if mixing is infinitely fast, you have to go back to what I told you just before, that the system goes to one of these three absorbing states, red, yellow, or blue. Let me show you the movies. This is what actually happens. That's the stochastic system. It shows spiral waves, and these spiral waves, they're not really smooth. They're rough, and the roughness comes from the stochasticity of the motion. You see this maybe even better when you look at the larger scale. This is the simulation of the stochastic dynamics using Gillespie on the lattice, and there you see you have these beautiful spiral waves. So rock, paper, and scissors coexist on this lattice, despite the fact that they would go extinct when you would not have a spatially extended system. Good, so far so good. Now let's try and put this all into equations. And let me just start this and then continue after the break. So we want to have a lattice. And let's take a square lattice for simplicity. Doesn't really matter that much what lattice you take, because the assumption you always make in these systems that the lattice is a vehicle to describe continuous space, and you don't expect things to depend on the lattice structure. It's an irrelevant degree of freedom. Okay? So what you say is that we have sites now, I and j, and let's say for simplicity we only take nearest neighbor hopping. So I and j are nearest neighbors. And I write this in the following as I twiddle j, indicating that those are nearest neighbors. And then I define a species dependent hopping rate. And I call this already D, right? So D is the hopping rate. In the end, it will become a diffusion coefficient in the macroscopic way for species sigma. And the hopping is from side I to side j. And similar as I did this before, for all these rates that we have, we take the state in which you go as the first index and the state from which you come as the second index. That has to do with the matrix structure of what we write down. So this means that I have here a species A, and instead of having a one index that indicates the nature of the species, it also indicates now the site at which the species is located. So here we have the site, and that's the type of species that we talk about. And that then goes to the same species, doesn't change its nature, but it goes to a different site. And now I guess you can see how this generalizes to what we had before. You just consider the species at different sites as different species, and then you're back in business with the original formulation. So the rate here is a rate connecting now these two types at a higher space. It also means now that the corresponding occupation number is having two indices, ni and sigma. That's the species, and that's the site. How would we choose the DIJs? Well, if you're non-equilibrium, then you can cook this up. Whatever you think is a proper diffusion constant, you take. And of course, the simplest case that you can imagine is that you have di to j sigma is the sigma, and you can make it even simpler and say all the different particles, types that you have in your lattice, they diffuse at the same kind of hopping rate. That's the simplest case. If you want to do something which contains interactions, then you have to think a bit harder, because now if you look at a lattice and you have a certain side I, then you might associate with this side I a potential ui of t. And this potential ui of t could be something you impose externally, because you say there's some gravitational potential, or there's some kind of flow that drags along the particles, or just some landscape where it's harder or not so hard to attach to that particular site. And that's encoded by this ui of t. Right? And then you can say, you write this dij, now assuming that our particles have the same diffusion coefficient, but that's not the point I want to make. You have to somehow say, how do you want this hopping rate now depend on the interaction that you have? If you're in equilibrium, then you know that there's detailed balance. So detailed balance means that if you have a rate going from j to I, then there will be a corresponding Gibbs-Boltzmann distribution at the side you start with. So that's the Boltzmann factor for a particle at side j with potential uj acting there. That has to be the same as the inverse hopping event with e to the minus beta ui. Okay? That's in general what you need to have. And all the reaction rates I write down that describe hopping, if they, as opposed to describe equilibrium dynamics, they would need to respect that detailed balance condition. But as you see, from that kind of detailed balance condition, you don't really fix the rates itself. All you fix is the ratio of the rates. So dij by dji is e to the minus beta ui minus uj. But you don't fix the individual rates. So you have a choice. And there's many choices you can make. Of course, if there's some underlying physics, you have no choice. But say this is the only constraint we have, then one possible choice for a hopping rate that respects detailed balance is such that I'm saying that this is the exponential of a half of the delta u that you have. So there is a difference in potential, and you're saying that you symmetrically say that the corresponding hopping rate pays that amount. And you can check, right? So if you take dij minus dji, where the delta u reverses sign, you get exactly the condition from detailed balance. Another one, that's one choice. Another choice you can make is the so-called heat bath rule. I guess basically because this comes from the same reasoning as in Metropolis, is to say that this is 2d divided by 1 plus the exponential of beta ui minus uj. What's a bit reassuring is that this choice doesn't make a difference if you are at linear order, and you can check this for yourself. If you are to linear order in the differences between ui and uj, those two expressions are actually the same.
Where does this come from?
It's a tutorial here in my, so I'm not supposed to tell you because otherwise you can't do the tutorial. But it's related to the same reasoning as in a Metropolis algorithm. Okay, so that's the motivation. And what we'll do after the break is we kind of forget at first about this thermodynamic constraint that you could have. And I will derive for you the corresponding path integral representation that includes just the dij's. And I'll perform this in a similar fashion as here, just now generalizing to spatial degrees of freedom. Okay, questions still? If not, let's have a break. Come back at 20 past.